Okay, so my name is Mazhar Memon, CTO and one of the co-founders of bitfusion. We're a company that just started a little over a year ago, so we're relatively new. We're based in Austin, Texas. If you guys are ever in town, please feel free to stop by. We like visitors. So I wanted to talk about this curve or these two curves, and it's the reason probably most of you are here, and it's the reason why we started bitfusion. And this is what I believe is the problem in computing today, right? So on the upper curve we have software, right? That is becoming increasingly abstract, and it's also slow. It's more demanding, right? Even with exponential increase in transistors, exponential increase in computing power, people are demanding an exponential increase in number of instances, exponential increase in number of cores. So something is quite demanding, and not only that, people don't write assembly anymore, and they are not writing as much C as they used to. Most graduates are using high-level languages and increasingly AI, meta modeling, right? The second curve is the hardware curve. And the hardware curve is something is happening, things are becoming more heterogeneous, and this is the pursuit of speed, right? Something's got to give. We can't do it with modern architectures. We need to do something architectural about it. And so this, I think, is the problem that we're facing, and the gap is widening. Software guys are becoming increasingly unaware of what the hardware is underneath, and the hardware guys are increasingly having a hard time catching up with software, right? Where you think you've sort of solved the problem with C, the next year someone's doing something with a brand new language. Now what do you do? So really delivering performance, delivering efficiency is just becoming harder and harder. This is another set of graphs that we talk about the software problem. On the right is a survey of the most popular languages, and you see that more and more there are more scripting languages. JavaScript, Ruby. We're now having languages that are specific to statistics, like R. You're coming up with new languages to take care of, or to actually extrapolate or extract parallelism from the machine. And on the left, you have the advent of machine learning everywhere. Like literally everywhere that anyone analyzes anything, there's some sort of machine learning thing. Every new startup has a machine learning sauce next to it, right? It's all about instead of automating the machine or physical labor, it's automating thought, right? So where does a human go at that point, right? Where all physical and mental thought is automated, then what does a human do, right? So things are happening very disruptively. And on the other hand, and you guys know this already, right? Transitional scale seems to be ending. We're starting to see a lot of cracks. With Moore's law, right? There's a technology curve which says that every 18 months, and now it's 2 years, and now it's 2.5 years. There's a double number in the actual transistor density. There's an economic point of view which says that the cost per transistor is supposed to decrease. There's a power argument with leakage, and there's also an engineering effort, right? When I first started at Intel, what was on the market was 90 nanometer processors, right? And I used to work in the factory, and so I would go to these process engineers, and they showed me, in the latest, the research fabs, what kind of transistors they're actually developing. It was 19 nanometers, from 90 to 19. That's how far in the future that to look to actually make 22 and 14 happen, this year and last. Right? So what people don't see, or what they think is sort of tick tock, they think that, oh, it just takes a couple of years, or it takes a year to advance a processor node. It actually takes more like 10 years, right? People have been probably working on 14 for a really, really long time. So this is becoming increasingly hard. And if Intel is sort of the Moore's law tick tock thing, right? Even their own architectures are increasingly heterogeneous. You're seeing so much more fixed functions being embedded directly into the pipeline. AVX instructions are heterogeneous, right? So what does this mean? You guys all know this as well. The way I like to look at this is, we started at sort of like the frequency wars, battles from the single megahertz to the single gigahertz, single digit gigahertz. The era of multi-core, where I hear people in that time frame say, I literally heard this: no one could possibly use more than 2 or 4 cores. So there's no point in adding more, right? We'd hear things like that. The era of many cores. Virtualization became very popular. Now you're thinking of having more than one user on machine. People are becoming, especially in HPC, much more savvy on parallel programming methods. And then the situation that we're sort of getting into is sort of the era of special core, where things like many cores are not good enough. There's a limited power envelope, there's limited sort of bandwidth, there's integration problems. Something has to give. Does the process technology actually give the economic value that it used to? I don't know. But what we see right now is a lot of people are creating their own chips, right? Google, Amazon, they're creating their own chips, right? MediaTek, China is trying to create an indigenous chip by themselves, right? The cost of actually doing business for a technology company in China is to do some sort of technology transfer, right? Like you can't sell into the Chinese market unless you're actually building, Chinese capability, right? They're also looking into developing their own chip for their next supercomputer. It's roughly like a VLIW, a DSP type thing. At least that's what the rumors are. Google, Amazon, Apple, these guys are thinking about vertical integration. And people who think about vertical integration, why not go all the way to the silicon, right? See Altera, Xilinx, Micron is coming out with the Automata processor. We have also other tile-based architectures that you can find. There's neuromorphic architectures. So there's probably about 10 logos I missed on this graph, but you get the gist, right? What I see is a lot of complexity here, right? And this is sort of unwieldy. So in short, era of frequency was easy for everyone except for the semiconductor company. But now, the complexity is going to more and more people. So this is, in my view, the way I look at things. And there's a big help exclamation mark here. I believe that, all of us probably in this room are trying to solve some of this problem, right? And this problem is so big and it's widening so much that there's just a lot of opportunity to collaborate, right? So there's like a famous quote, right? Henry Kissinger says, when there's so little at stake, there's so much competition, right? Like with the university professors, this is like the opposite problem, right? There's so much at stake, right? And that's where collaboration needs to happen, right? So solutions, at least the way I see it, is you need to basically make these two curves try to converge against each other. On the hardware side, specialized hardware is really hard to deal with, right? You have to use it, but you have to make it accessible. At least allow developers to use them, right? So price, especially for new architectures, right? If you're thinking about quantum computing, like how many millions of dollars do you need to get access to quantum computer? Maybe like $20 million? I don't know, right? There's other architectures that haven't been delivered at volume. You may need 10 to 20K, right? FPGAs, you need, what are there, like a high-end one, what is it, Fernando, like 2 to 5K, right? A GPU, like maybe 1,000, maybe up to 5,000 for the K80, right? So as you go sort of in the future, the more heterogeneous, the more specialized, they become really expensive. So we need to encourage accessibility somehow. In terms of software, it's really about, at least what I believe is, it's libraries, APIs, really the tool chain, right? So that's why we're really excited about SDXL and the work that Altera has also been doing in supporting OpenCL. Getting something that looks like C all the way to gates is really a profound thing if you think about it, right? So supporting actually developing a tool chain that goes all the way to compiler level IR, I think that is like minimum, because if you can go to a compiler level IR, that means that you can now support a lot more languages. Use translations where possible. This is an important one. Oftentimes when you do performance optimization, think about who has developed with CUDA or OpenCL. Show of hands. Okay, very few. Has anyone done like any sort of parallelism, like OMP, like multi-threading, right? Okay, so anyone who's done any sort of parallelism work, right? What you end up doing is you're injecting pragmas. You're changing the architecture of the beautiful algorithm that is the fundamental thing that you're trying to accomplish, right? So the guys from TMT, right? They showed the matrix multiplication, right? And how it's very simple in their syntax, but if you were to implement it in a very optimal way, you're polluting like the essence of this algorithm with what the underlying architecture is, right? So imagine if you had a really optimal matrix multiplication thing for CUDA. That does not look like matrix multiplication anymore. It might be like 10 times longer, a lot of complexity. You have to squint really hard to see that that's actually a matrix multiplication. That's one of the problems of developing for high-performance hardware, is the essence of the algorithm gets lost. And it becomes very, very hard to move that algorithm to another architecture, right? It becomes very sticky. So any sort of translations that are possible, please do that. An ecosystem, this takes a lot of money, right? Learning materials, conferences, a lot of marketing, university engagement. This is all sort of like boring stuff, but a new hardware vendor, actually has to do all this stuff. And really the engine that I believe, drives all this is developers, right? Enabling developers. And so developers have to find some sort of compelling reason to try new hardware. They also have to be supported. So the focus on this talk is really about developers. And I'm just going to touch on, I guess, 4 or 5 different architectures and sort of talk about them. This is sort of what we think is the developer experience. Very unhappy. So you have issues like this. So vendor tools only support a specific operating system. I have a Mac. I want to, work on a DSP. How do I do that? Well, that DSP vendor is going to support some old version of Linux that no one has used in the past 5 years, right? The tool flows, make them as open and accessible as possible. Setting up environment licenses, right? Like literally, if you wanted to, in a lot of cases, create a custom solution, you have to talk to 5 different people, get licenses from everyone, and then integrate it somehow and figure out if it actually works, right? Licensing is really a big hurdle. There's hardware installation. The scientists, right? Imagine if they had to install hardware themselves. It's just a pain, right? Numerous pages of documentation. Do you really want to read 50 pages of documentation to learn how to use your hardware? So the developer experience, especially new hardware, is really, really, really hard, right? No good. So I'll start with integrated GPUs because most of us here probably has an integrated GPU. How many here have used their integrated GPU? Do you know that you have an integrated GPU? Okay. How about like a discrete GPU? Like CUDA, OpenCL? Okay, cool. FPGAs? Cool. Feels like the same people raising their hands. Anything else? Automata? Okay, cool. All right, so the way I'm going to explain these examples is, so integrated GPUs, right? So these are GPUs that are integrated tightly with in the CPU complex. So if you look here, you look at an Intel processor, you have a whole bunch of normal CPU cores, and attached to it is several execution units, right? So this is kind of like CUDA cores kind of thing, right? And what's cool about integrated architectures is you can reuse a lot of the architecture, right? You don't have to have your own memory controller. You don't have to have your own interconnect, right? You don't have to have your own PCIe interface. You don't have to have any of these. You don't have to have page walkers. You don't have to deal with IO memus or virtual memory, right? Page walking. All that stuff can be really reused in a CPU complex, right? Scratchpad memory. You could use caches, right? So integration saves a lot of gates, right? It's a really an efficient way of reusing a lot of the architecture. The downside, of course, is the real estate on this die is really, really expensive, right? So that's why these things are never that big, right? It's classic SIMD architecture, single instruction, multiple data. This is typically medium-sized offloads, maybe small to medium-size, right? You're probably not going to have a great experience gaming. Very latency sensitive workloads, right? So if you want to get something done really, really quick, some small amount of computation really, really quick, it's very latency sensitive. This is a great architecture to try that. It looks like this kind of architecture is pretty popular in media transcoding. And programming models are, these are the main ones, I believe. OpenCL, Direct Compute, C++ AMP, Spear, HSA. Has anyone heard of any of these? Kind of? Okay. So OpenCL is probably the most common one. I think that if you're a developer in general that's looking at sort of SIMD kind of architectures, you guys should read up on Spear. Spear is sort of it's an IR, an intermediate representation that is compiled from a wide variety of other languages. So OpenCL will compile to Spear. Any new like C++, like 17, will also compile to Spear. And you can create your own language and compile it to Spear. It's a great sort of standardization layer, if you will. I'd say ecosystem maturity is pretty high, and right, AMD is very interested in sort of this heterogeneous integrated approach. Next one is discrete GPUs. You guys are probably familiar with this, right? This is not integrated. It's still SIMD. It's in a discrete co-processor configuration. What that means is there's a host. Your host machine is connected, through PCIe to this GPU. The GPU is not a master. It's a slave, right? The host tells it what to do. Your software tells it what to do. This is geared towards throughput sensitive workloads. You have to have a lot of computation for this to make sense. A lot more computation per byte. Programming models. The new one is CUDA. Another one to look out for is SYCL. It's another Kronos standard. I think it's probably going to take many years for that to be, very popular. But is essentially changes to C++ for it to be sort of in one file you have code for the GPU, code for your CPU, all in one code base, kind of like CUDA, the CUDA runtime API. Ecosystem maturity, I think, is probably medium high. There's a lot of innovation here happening from the Kronos group. So again, I would look at Spear, and I think CUDA, obviously, most widely used GPU API. Mix. So Mix this is many core architecture. So this is also in a co-processor configuration. So this would be like a card that you install in your server, and it's also for large offloads, throughput sensitive, and it's not really a SIMD kind of thing, although it has a lot of SIMD hardware on it. It's mainly geared for generic HPC. You see these a lot in supercomputing, so it's pretty popular. It supports multi-threading with OpenMP, MPI, and just general x86. So when you install this in your server, basically you SSH to it. So like in this card is like a Linux distribution, right? You say top and you see a whole bunch of cores, right? And you can generally you can run most any x86 code. The cores in here are based on the Atom processor, low power, not highly out of order, but there's a lot of them, right? I think as a developer, one thing to keep in mind is, as I said before, integration is like name of the game in semiconductors, right? Integration makes a lot of very interesting things happen, right? What I mean by that is if in this processor here where you have a whole bunch of like low power cores, you put in a Xeon, like a server class Xeon CPU, this whole thing becomes bootable as like an independent node. And that's really powerful, right? You can run Linux, you can run your database app, and it's all running in this coprocessor. That changes everything, right? Because now you're not talking about data transfer between the host and the coprocessor. This becomes like a first-class citizen. So imagine if you had like 8 of these in your machine, right? Now they're talking to each other in PCIe. I believe that, you know, I'm sure IBM and NVIDIA and Mellanox are thinking maybe around that area. I don't know. But that would also be very interesting, right? Let's see. The other thing that's being integrated into Knights Landing is the fabric. So in this coprocessor, you might start seeing a network port on this, right? So imagine 200 gigabits a second coming to this coprocessor. That becomes very interesting, right? Now you can do offloads like you couldn't before. So this is one to watch out for. Obviously, this is all like, you know, theory. It's all on execution in semiconductors, right? We could easily see something very interesting from, you know, IBM and NVIDIA. FPGAs, we already talked about them. Fernando's the expert. He's right there. So FPGAs are very cool, reconfigurable, obviously. A lot of very cool things have happened with you know, enabling of OpenCL. So definitely something to watch for. It looks like it could become mainstream in cloud in sometime in, you know, next 5 years. Definitely something to look out for. This is one I want to talk about. So Automata is a, have you guys heard about Automata processor? Yeah, from Micron. So this is like a way out there kind of architecture. So remember I was saying that the expensive it is, the less mainstream it is. Well, one of these cards is $20,000. So it's way out there. I don't expect, you know, high volume anytime soon. Okay, so there's this theory that every computer language, whether it's Java or C++ or whatever, can be represented in something called a context-free grammar, right? You could write a set of rules and you could explain all of that language in a simple grammar, just like you have a you know, grammar for different languages. So just, you know, in computation, you guys have heard of Turing complete. That's sort of like a fundamental thing of completeness of an architecture. Context-free grammar is sort of like completeness of expressiveness of a language, right? So a context-free grammar can always be represented in something called an NFA, a non-deterministic finite automata, right? And it's just it's a kind of state machine with certain properties, right? And every NFA could be represented by a DFA, which is discrete finite automata, and it's also a finite state machine that that will always end deterministically with a deterministic input. So an NFA, think of this as a state machine. And the state machine is composed of these elements called STEs. They're state transition elements, right? And as you get an input, you decide if you transition to the next state or not, right? So you just have matching characters, and you have these rules, and you can describe whatever your algorithm is based on certain rules, based on your state transition, right? And this fabric has basic like Boolean logic. It has some counters to do some mathematical operation counting. And if you look on Micron's site, you can actually see a nice little simulator where you can actually you know, create your own finite state machine. So what's cool about this is originally they were thinking of putting these state machines in a DIMM, in a memory like a DIMM. Like you could put this in your, like instead of 64 gigs, you take out one DIMM and put one of these in it, and it becomes a programmable processor. Well, because the JEDEC spec doesn't allow that, there's no way to have interrupts in your slot. This was really not possible, so they went with the PCI config and sort of the same sort of code processor configuration. So this is an interesting one. The kind of workloads that are interesting are basically regular expressions. Regular expressions, that's another thing that could be represented in NFA very efficiently. It's good for pattern matching. So do you know this guy? Is he here? Dave? What's his name? Okay, so this kind of thing is great for fuzzy matching, which is computationally hard for standard architectures. So that's sort of touching on what I think are sort of the up-and-coming architectures, potentially, at least the interesting ones. What does this mean, right? You have all these architectures. You can go onto the websites. You can get some getting started guides. Really, the accessibility is a problem. Imagine yourself wanting to try any of these, right? These things are pretty expensive. It'll take quite a bit of time to even set up. So when I was talking about sort of that widening gap, we want to be part of the solution, and so we stick ourselves in this widening gap. And the problem that we want to solve is we want to develop software that can translate the value of high performance hardware to your software, right? Make it as easy as possible. Basically, add layers of abstraction, and this is what we mean. So, one of the fundamental problems that we wanted to solve is that one can spend a lot of time to port your code to another architecture, but getting performance from that, getting additional scaling from that becomes difficult, right? You have an application that you've coded for a single GPU. You want to now use all the GPUs in your cluster. How do you do that? Well, it's a basically iterative approach of doing some performance optimization. So here are three different kinds of scaling that we try to enable. One is sort of the heterogeneous system, automatically going from a CPU-based system to a GPU-based system. Vertical scaling, making a single device application to a multi-device application, right? So you can scale within the machine. You can take advantage of 4 GPUs or 8 GPUs in the same machine. And then horizontal scaling or scale out, taking advantage of all the GPUs in all remote systems. So we've enabled all of this, and we tried this across different applications, and we've had pretty good success across rendering, computational science, computer vision, image processing, machine learning, and rendering, going from like 1 to 4 local GPUs, right? So depending on the kind of scaling that you're interested in, we've tried across different scenarios where you're in the cloud and you're on a low-cost instance. How can you scale and get that access to a GPU? But the question is, so all this, how is this possible? I don't know how much time we have, but the way this works is this is the view that we want. This is the view that we want the application, the user to see, which is just their application. And all they see is one abstract view of their hardware, right? This is the application that we want to see. Under the covers is a whole bunch of complexity, right? You have to make things performant. We intercept certain APIs. We split both the data and the computation across both the local resources and also across remote resources. We have a mechanism to do server discovery. So basically, we try to make this as plug and play as possible, and also have the ability to introduce libraries that are specifically optimized for your architecture. So let's say you're using that FPGA, and it takes 4 hours to create a bit stream. While you're creating that bit stream, you could target the local CPU that's running OpenCL. When that bit stream becomes available, you plug this in. You don't have to tear down the application, and you just run faster. So we talked about scale out. That's one of the problems that we're trying to solve. What if you do scale in, which is have multiple microclients that share an expensive device, right? So imagine you had an HPC hardware that costs $10,000. Obviously, you can't have that on multiple machines. You're not talking about performance. You're really trying to enable people to start using it, porting their applications. And so what you could do is you could have these really inexpensive, small, maybe 1 core, 2 core kind of machines, and you can access these devices remotely. So this has an economic advantage, right? You can now support multiple users, enable them on an architecture, and help to solve the accessibility problem. And so this is this is basically that the announcement of Nimbix and bitfusion working together, really providing low-cost instances for people who want to work on GPUs. So yeah, hopefully you guys try it out and give us some feedback. Any questions? Yep.
Thank you. In the case of scale-in, when you were talking about sharing resources, I'm just wondering, in the case of, say, CUDA specifically, how you would deal with competing kernels of different sizes that are executing on the card, because obviously some kernels can be quite long-running and some be shorter. There's obviously a time limit with CUDA, but how they interfere with each other.
So, so that's a good question. So there's two levels of scheduling. You can have multiple users target the same server. In that case, we do first scheduling to the actual devices in the number of requests. So if you have one request, two requests, we basically, it's a fair scheduler. The CUDA runtime is really the one that does this micro-level scheduling, right? So, and I think CUDA 7.5, they do much finer-grained scheduling where you could use some, some part of some CUDA course for some application, other CUDA course for the other application. It figures out how to dynamically provision it. It's one of the new features in 7.5. I would assume it becomes better as time goes on. That's one of the fundamental things, is that we're not solving a vendor problem, right? So using the multi-tenancy at a micro level, that has to be solved by the vendor. That's really the most efficient way to do it.
So one thing, sorry, I did want to say one thing about the new machine types is that we also, and we haven't actually tested any code this way, but we also enable OpenCL scale-in, right, with the same exact machine type. So we're kind of leading with CUDA as that seems to be very popular for machine learning and so forth. But you can also do OpenCL on the client side and get the same with the same basic economics, right?
Exactly.
Thanks. Mazhar, how do you envision kind of, you mentioned the application view and the abstraction, and I kind of have a relative understanding with CUDA, for example, or OpenCL, and maybe that's the answer. But tell me, I guess, how would this work in the context of FPGAs, for example, and how does the application, relative to the other things we heard today about SDXL, how can we leverage that to jointly?
So we've done a lot of tests. Actually, before we enabled GPUs, we enabled FPGAs. Actually, we started with Altera ones, but we also enabled with SDXL. It's the same concept. So what would the applications use? OpenCL. We intercept OpenCL and we remote all those calls to the server. Now, if I look at like this picture here, on this side, this is where SDXL lives. This is where all the FPGA tools live. This is where the compiler, the offline compiler lives. None of that is on the client machines. This is where the application lives, right? So the application is completely segregated on the client side, and the vendor tools, SDXL, is all on the server. So that's one way of really simplifying things, because on the left-hand side, we could be a Windows machine. We could be a Mac. Right, you could be like whatever architecture, because OpenCL is a standard, right? And as long as we remote that, you don't have to expose, for example, CentOS or a Linux distribution that a developer is not familiar with, right?
Any other questions? All right. Well, thank you very much, Mazhar.